Hi, George Diamond here. Today we're going to take a look at extreme values of functions. Now in our textbook this is section 3.1. So we are starting chapter 3 in the Larson text. Now this is video number 1. Now you probably noticed that I have a blue container of Maxwell House coffee. This has nothing to do with the video, but I teach AP Calculus and my students need to document anything that's unusual in my video. So we're going to set this to the side and let's get started. So now this is video number 1. Now, video number 1, all I've done is put together some information on a little PowerPoint talking about some key vocabulary, some key concepts involving extreme values on a function, particularly maximum minimum on a closed interval. So let's get started. Now you won't see a bunch of examples in this video, almost no examples. Now video number 2, okay, we're actually going to find some critical numbers, we're actually going to find some maximum minimum values on a closed interval. So you want to look at my next video if you're looking for a bunch of examples, all right? But in this video we're not going to have any examples. But to get started, a couple of essential questions that we're going to kind of introduce as we get started here. The first one says, how can you find the maximum minimum value of a point of a graph on a closed interval? How do you find maximum minimum on a closed interval? Now we're going to be talking about that, kind of discussing it here. We're actually going to work some examples on the next video. Number 2, what is the difference between absolute and relative extrema? All right. And the third essential question, how do you find the critical points of a function? So we're going to look at finding the critical points today. It's a very important concept and that you have to be able to do when you're working with maximum minimum. So let's start off introducing the extreme value theorem. Now in our textbook this is Theorem 3.1, but this is called the extreme value theorem. Now what the extreme value theorem says if f is a continuous function on a closed interval. All right, now two key concepts. The graph has to be continuous, so no jumps, no gaps, no asymptotes. And it's going to be on a closed interval. That means that the endpoints are included in the domain. Right. Then the function has to have both a minimum and a maximum value. All right, so once again, if it's continuous on a closed interval, okay, that function will have a minimum and a maximum value on that closed interval. So that's what the extreme value theorem says. Now, when we talk about a little bit of vocabulary here, the first term we want to notice here is what an absolute extreme is. And this is either a maximum or minimum points on a curve. So the highest or the lowest point on a curve. Right? And these are also called absolute extrema, which is plural for the Latin extrema. Right? So they're also called the absolute extrema. Okay, next. Now extreme values can occur at interior points or at endpoints. Now if it's on a closed interval, okay, that means the endpoints are included in the domain. So the endpoints can be maximum or minimum points. So extreme values, they can occur at the endpoints as well as in the interior points of a curve. Now, functions with the same defining value or the same defining rule can have different extrema depending upon the domain. So if you change the domain, you can have a different minimum maximum value if you restrict the function in a different way. Right? So by restricting the domain. So let's take our first example. Now extreme values can be in the interior or at the endpoints of a function. Now the first example here, we're going to use this here as our defining rule, y equals x squared, just a little parabola. Okay, we're all familiar with our parabolas. Now this is now on our parabola here, we're not restricting the domain at all. Let's say the domain is from negative infinity to positive infinity. So when you look at our graph, right? So here's our graph. You can see it here on our PowerPoint. You can see down here at 0, 0. 0, 0 would be, in this particular curve, would be the absolute minimum. There is no point on the curve that's lower than 0, 0. So that's called the absolute minimum point. Now, this particular curve has no absolute maximum though. So the curve keeps on going up to infinity. So it keeps on going up. So it has no absolute minimum, but it does have has no absolute maximum, but it does have an absolute minimum point. So the absolute minimum here is 0, 0. So you can see by not restricting the domain, okay, the curve keeps on going upwards to infinity. All right, so the domain is from negative infinity to positive infinity, so it has an absolute minimum and an absolute maximum. Now, in the next slide, Okay, we're going to restrict the domain a little bit. Okay, same defining rule, y equals x squared. Now this time we're restricting the domain. Okay, we're only going to look at the part of the curve from 0 to 2. Now 0 and 2 are closed. That's a closed endpoints. So you can see the solid dot at each endpoint here. So from 0 to 2, this is the part of the curve we're talking about now. So now we're talking about maximum minimum on a closed interval now. So from 0 to 2. So as you look at this now, remember on a closed interval, the endpoints can be maximum minimum points. So as you look at this particular curve, because the endpoint here is part of your domain, so you can see it's shaded in, we got a solid dot basically, okay, this becomes an absolute minimum. And now at the other endpoint up here, this becomes an absolute maximum. So once again, x equal 2, okay, this is the other endpoint here is part of our domain, so therefore it's closed. That means that this point up here can be and is a absolute maximum. So on a closed interval from 0 to 2, 0 and 2 included in the domain, you can see other shaded, you have an absolute minimum and we have an absolute maximum. And the endpoints are, one of them's the minimum, the other one's the maximum. Now, let's change the same defining rule again. Now this time, let's change the domain a little bit. Now the domain this time is from 0 to 2 again, but this time 0 is not part of the domain. You can see this is open at 0 and closed at 2. So 2 is still included in the domain, but 0 is not. All right, so as you look at the graph now, that would be an open at 0, 0, all right, and then closed at x equal 2. All right. Now this time, since this is open at the endpoint, this endpoint cannot be a minimum or maximum. So in this case, by restricting the domain this time, there is no absolute minimum on this curve. Okay, because the left endpoint here is not part of your domain. So if you could imagine this, because 0 is not part of your domain, you can just keep getting closer and closer and closer to that open dot, if you will. All right. So really there is no, it says there's simply no absolute minimum here, right? Now at the other endpoint, now this endpoint is still part of your domain, so 2 is still part of the domain, so this is still an absolute maximum. Now look at another one. Okay, let's change the domain a little bit more. Now this time let's let, once again the domain is from 0 to 2, but it's neither 0 or 2, neither one of them are part of our domain this time. So if you look at your graph, that will be an open dot at 0, open dot at x equal 2 at the other endpoint. Now remember now, if the endpoints are included, they can be maximum or minimum. So in this case, 0, x equals 0, x equal 2, these two endpoints now cannot be maximum or minimum. These are not part of the domain. As you can see on the graph, there'll be an open at each of those endpoints. So this is open here. So this particular graph now, because the domain is 0 to 2, open at each end. Okay, we have no minimum at 0 and no minimum at x equal 2. So this has no absolute minimum and no absolute maximum. So no minimum, no maximum. Okay. Now let's go ahead. Now when we talk about the extreme value theorem, we just looked at it on the previous slides. Now once again, it has to be, remember, it has to be continuous and on a closed interval. So if it's continuous and closed, then it has to have an absolute minimum and an absolute maximum. Now, there's three things really that can happen as you look at the maximum minimum. It could be you end up with something like this little curve here. As you look at this curve, you've got an endpoint here. That's the other endpoint. Now, once again, imagine now this is a closed interval, so neither endpoint is an absolute maximum or minimum. So on this first little curve, the absolute minimum and maximum occur in the interior of the function. So they're both in the interior. So neither endpoint is going to be the highest or lowest point on the curve over that interval. So as you look at this, the maximum minimum occurs at the interior points. So it's very possible. If you got two critical points like this one here would have, or two, the hill and the valley kind of, okay, you're going to have the maximum minimum points will occur in the interior of the function. Now, it's also possible you can have this type of a graph as you look at the closed interval. Right? Now, once again, the endpoints are closed. So in this particular case here, one of your endpoints will be a maximum, the other endpoint will be a minimum. Right? So the interior the interior of the function, there's no minimum or maximum point. So in this case, in this particular case, the maximum and the minimum points will occur at the two endpoints. So this would be your maximum, this would be your minimum. Now, it's also possible we could have something like the third instance down here. Now, as you look at this third case, you can see this is the lowest point on the closed interval on the graph would be the absolute minimum here. But in the interior of the function, you can see this point up here is the highest point on the curve. So in this particular case, the absolute minimum occurs at an endpoint, but the absolute maximum occurs in the interior of the function. So you have a maximum at an interior point and a minimum at an endpoint. So basically three cases that you can have. Minimum and maximum occur in the interior. It's possible that the two endpoints could be your maximum or minimum. And it's possible that one endpoint could be a maximum or minimum, and the other could be max or minimum could be at in the interior of your function. So one of these three cases is going to happen. Now, also let's talk about relative extreme values, right? So relative extreme. Now, a relative, what's called a relative, some textbooks call them a local extremum or maximum value. Okay, this is simply the maximum value on an open interval, right? So maximum value on an open interval, we call it a relative maximum. So that is, it's not the highest point on the curve, but it's a high point. It's not the highest, it's simply a high point. It would be like maybe a hill within a particular neighborhood of the graph. But it's not the highest point on the graph. Right? So a relative maximum would simply be a high point. Not the highest point, though. The highest point is going to be the absolute maximum. All right? Now, a relative minimum, sometimes referred to as a local minimum. Okay, this is simply a low point on your curve, not the lowest. Remember, the lowest point is going to be the absolute minimum. Okay, now a relative minimum is simply a low point, not the lowest though. All right? So not the lowest. So, take a look at this curve right here. Okay, now you can imagine this is on a closed interval, so the endpoints here are included in our domain. So this will be on a closed interval. And you can see what the curve is, what it's like here. It goes up and down, generally increasing from left to right for the most part. So as you look at this graph, you can see right here on the left-hand the left-hand bottom point here, on the left-hand side of the graph, this right here is the lowest point on the curve. Now, so this particular graph, this is going to be the absolute minimum. There is no point on the graph lower than that one. All right, so this here is the absolute minimum. Now, if you look right here, okay, this is like a little hill. This is called a relative maximum. It's not the highest point on the curve. This point over here is the highest. Okay, this here is not the highest, but it's a high point. So the graph goes up and starts back down. So it's like a little hill on your graph, basically, right? So once again, this is called a relative maximum, not an absolute maximum. Okay, next you notice that we take a little dip right here. Okay, this point right here is called a relative minimum. So this is a relative minimum. In other words, it's not the lowest point on the curve, it's a low point, like a valley kind of on your graph. When you look at your graph, this will be a relative minimum. This down here, though, is the absolute minimum. So there's no place right here on the graph that's lower than the absolute minimum. This is a relative minimum. Now, if you look up here, that's our absolute maximum point on our curve. That would be the absolute max. There's no place on the graph, on my graph, that's higher than that point there. Now down here, the other endpoint though is a relative minimum. It's not the lowest, it's just a low point on the curve. You can see it's decreasing here, it's simply a low point. So once again, now a couple things I want you to notice about the graph, where relative minimum and relative maximum points occur on the interior of a function. So relative extremas are also called local extremas. So some textbooks, depending upon your textbook, your book may call it a local maximum or a local minimum. Okay, our textbook uses relative maximum, relative minimum. Right. Now also you'll notice that the relative extremes in the interior of a function always occur where the derivative is equal to 0 or where the derivative doesn't exist. So for instance, you look on this graph right here, you can see if you draw a tangent line to the curve here and here, you can see that the slope of your tangent line is 0. Slope of this tangent line is 0. Okay, that means the derivative would be equal to 0 at each of these points. So at that point and this point, the derivative of this function would be equal to 0. Now, you also notice now we got an absolute maximum point at this point, at the main top of the curve up here, at this point. Now, there's no horizontal tangent line at this point here. It's a sharp corner. So remember we said the derivative doesn't exist at a corner, at a sharp corner, or at a cusp. It comes to a point like that, the derivative doesn't exist. So at this particular point here, the derivative does not exist. DNE for does not exist. So in the interior of a function, okay, relative maximum minimum points only occur where the derivative is equal to 0 or where the derivative doesn't exist. It's going to be one of those two. If it's an interior point on the curve, it has to be a place where the derivative is equal to 0. That would indicate a horizontal tangent line at that particular point. Or it could be a place like we have at the top of the curve. It could be a point where the derivative doesn't exist. There's no horizontal tangent line, but the derivative doesn't exist at this point, but it's still an absolute maximum point. All right. Next. Now, these are called critical points. So let's go ahead and talk about critical points too. Okay, this is a point in the domain of a function, f, right? Okay, where the derivative is equal to 0 or where the derivative does not exist. So a critical point. Two things, is where the derivative is equal to 0 and where the derivative does not exist. All right. Now, a couple things to note. I kind of listed this on my PowerPoint, so I want to talk about it a little bit. And this is important. Maximum and minimum points in the interior of a function always occur at critical points. All right, so let me circle the word always. Always occur at critical points. But all critical points are not necessarily maximum or minimum values. All right, so once again, this is important. If it's a maximum or minimum in the interior of a function, it will be at a critical point. But not all critical points are going to be maximum minimum points on a curve. There may be places on the curve where the derivative doesn't exist, but it's still not a maximum or minimum point. All right. So once again, remember now, maximum minimum points on in the interior of a function always occur at critical points. Okay, but critical points, all critical points are not necessarily maximum minimum points. All right. So just kind of keep that in mind about the critical point on a curve. So the critical point is where the derivative doesn't exist. Now when I say the derivative doesn't exist, that means there will be a horizontal tangent line to the curve at that point. Okay, or where the derivative is equal to 0, you have the horizontal tangent line, or it could be where the derivative doesn't exist. So it could be a corner or a cusp of some type on your curve. So, some guidelines for finding the extrema on a closed interval. Now once again, when I say closed interval, okay, that means the endpoints can be included in your graph. Now I teach AP Calculus, and one of the biggest mistakes students make when they take the AP Calculus exam at the end of the year, if they're asked to find maximum or minimum points on a curve, they'll look for the critical points and they forget to check the endpoints. Right, but remember, if it's on a closed interval, the endpoints have to be checked. Now, so some guidelines for finding maximum or finding extrema, maximum or minimum points. Number one, okay, evaluate the function at the endpoints. So find the endpoints first. Remember now, the endpoints can be maximum or minimum points. Okay, so you're going to have to evaluate the endpoints. I can go ahead and do that first if it's a closed interval. Number two, find all critical points, or all critical numbers we call them, right? So find all critical points on the curve. Okay, number three, evaluate the function at each critical point in the closed interval AB. So once you find your critical point, you've got to evaluate that by plugging it, substituting it back into your original function, and then you can evaluate it. Now, the least is going to be the minimum, so the least value is going to be your minimum, and the greatest is going to be your maximum value. So, once again, let's summarize. Guidelines. Number one, find your endpoints. Number two, find your critical points within the closed interval. Because remember, critical points can be maximum or minimum points. And so can the endpoints. evaluate the function at each critical point. So once you find the critical point, or the critical number, okay, you got to substitute it into the original function to find your corresponding y value. All right, so you're finding the actual point. And remember now, the least is the minimum. Now when I say the least, you're going to compare their y values basically. So the y values would be their location on the y-axis, so you got to check their y values to see which is the greatest and which is the least. All right, and we'll do video number 2. You can kind of watch video number 2 for some examples.